Assalamu alaikum, dear student. This is Muhammad Mahawalam, lecturer in chemistry, Rajagutra Model College, English Medium Day Shift. So today I would like to deliver a very important lecture on organic chemistry. This is my third lecture on this chapter. In this lecture, I would like to deliver speech on different topics. For the first time, I would like to say something about the orbital structure of the benzene. You know very well the molecular formula of benzene is C6H6, and this is the structural formula that you have seen in the board. Okay, this is clear to you that each of the benzene ring contains 6 carbon in addition with 6 hydrogen atom. From its structural formula, this is clear to you that. Again, this is basically the orbital structure of benzene. The point that you must have to remember in that case that each of the carbon atom of benzene are sp2 hybridized. As each of the carbon are sp2 hybridized, so there presents 3 sp2 hybrid orbital, and out of these 3 sp2 hybrid orbital, 2 sp2 hybrid orbital will form 2 sigma bond with the adjacent carbon, and the other hybrid orbital will form a sigma bond with the s orbital of hydrogen. So by this way, 3 sp2 hybrid orbital will form 3 sigma bond. By this way, you will get a hexagonal planar structure. Now there still presents a unhybridized 2pz orbital, which one is perpendicular to the hexagonal planar of the benzene ring. Okay, as there present 6 carbon, so each of the carbon are sp2 hybridized, so there must present 6 unhybridized 2pz orbital, which one presents perpendicular to the planar hexagonal structure. Okay, you know very well the unhybridized 2pz orbital or p orbital have the capability to overlap sideways fashion, and they can form pi bond. Okay, so as there presents 6 2pz orbital, so they can form 3 pi bond. From this structure of benzene, this is clear to you that there are 3 pi bond present in this structure. The point that you have to notice in that case, this pi bonding electron should not be restricted in between these 2 carbon or 2 carbon. The pi bonding electron should be delocalized. In that case, in case of benzene, the pi bonding electron have the capability to delocalize throughout the benzene ring. As they are in delocalized state, they are produced pi bonding orbital. Which one is present above or below? Which one is present above or below to the planar hexagonal structure? So you can say that the structure of benzene is basically hexagonal plate planar structure having pi bonding orbital above or below the planar hexagonal structure. Okay, so in that case, the point that you have to notice that pi bonding electron or pi bonding electron cloud should be present above or the below the planar hexagonal structure. Okay, due to the resonance or due to the delocalization of these pi bonding electron, there are more structure can be possible in case of benzene. You have seen on the board, this structure is also possible if there is a resonance, if the electron can be resonate by this way. So you can also have this structure, and this is the hybrid structure. Okay, this is the combination of these two structures. This is the hybrid structure, where this indicates the resonating of 6 pi electron. Okay, this is basically the information about the orbital structure. Now, due to the delocalization of pi electron, what happened? Due to the delocalization of pi electron, the unsaturation of benzene is basically different than the unsaturation of alkene or alkyne of aliphatic compound. You know, aliphatic compound, due to the unsaturation, it can participate in addition reaction, right? But in case of benzene, due to the presence of unsaturation of benzene, it cannot only participate in addition reaction, it can also participate in substitution reaction too. But aliphatic unsaturated compound cannot have the capability to participate in substitution reaction. You know, in case of benzene can undergo electrophilic substitution reaction, nitration, sulfonation, chlorination, halogenation. Number of electrophilic substitution can be possible in case of benzene, though their presence unsaturation Okay, at the same time it can also undergo addition reaction. You know, hydrogen addition is possible here, chlorine addition is possible here, ozone addition is possible here. So basically due to that, this is possible due to the delocalization of the pi electron above the below of the planar hexagonal structure. And again, in case of benzene, the structure, again in case of benzene, this is clear to us that the carbon-carbon bond length is 0.139 angstrom. Okay, in case of aliphatic compound, the carbon-carbon bond length is 0.134 angstrom. So the bond length is basically in between the carbon-carbon. You know very well the carbon-carbon single bond length is 0.154 and carbon-carbon double bond length is 1.134 in case of aliphatic compound. And in case of benzene ring, carbon-carbon double bond or carbon-carbon single bond length is basically in between the carbon-carbon single bond and carbon-carbon double bond of aliphatic compound, which one is 0.139 angstrom. I would like to say at the end of the topics that due to the presence of delocalization of the pi electron, again say due to the presence of the delocalization of the pi electron, basically there happen the benzene ring become more stable. That's why it can undergo addition reaction, it can undergo electrophilic substitution reaction, and the bond length is basically in between the carbon-carbon single bond and carbon-carbon double bond of the aliphatic compound. So the main point to be noted here, the structure of benzene is hexagonal planar structure having delocalized pi bonding orbital above or below the planar structure. So dear student, now about aromaticity and Huckel rule. For the first time I would like to say something about Huckel rule. Huckel rules are basically the necessary condition that is proposed by Huckel to determine either any compound aromatic or not aromatic. So the rules to determine the aromaticity is basically called Huckel rule. And these are the rules of Huckel. The first rule, the system should be closed system. The structure should be closed system containing more than 5 or 6 carbon atom normally. So to become any compound aromatic, the structure should be cyclic closed structure. Okay, and this structure must contain normally more than 5 or 6 carbon. Okay, now the second concept, each of the carbon atom must be sp2 hybridized, so system should be conjugated and have planar structure. This is very important concept. To become any compound aromatic, each of the carbon atom must be sp2 hybridized. Here the point that you should be noted that if in any structure all the carbons are sp2 hybridized, then the system automatically become planar. At the same time, the system automatically become conjugated. So any system, if it is conjugated, if it has planar structure, if all the carbons are sp2 hybridized, so this structure can be a aromatic structure. Now the concept C, as all the carbon atoms are sp2 hybridized in case of aromatic compound, so each carbon must contain an unhybridized p orbital, right, which one should be perpendicular to the planar structure of the aromatic system. These unhybridized p orbital should overlap each with other sideways fashion. By this way it can form pi bond and a pi bonding orbital. This pi bonding orbital must contain pi bonding electron, and in that case this is mandatory to say that if any system wants to be aromatic, this pi bonding orbital system must contain 4n+2 numbered pi electron, where the value of n can be 0, 1, 2, 3 different positive integer. It cannot be fraction. Okay, if you put the value of n is equal to 0, then you will get 2. So 2 is a Huckel number. If you put the value of 1 here, then you will get the value of 4n+2 is equal to 6. This is also a Huckel number. If you put the value of 3, then you will get the Huckel number 14. So 2, 6, 10, 14, these are basically the Huckel number. So if this number of pi electron can be present in any system, in that case you can say this is the aromatic system. Now D, if any system contain heteroatom, for example nitrogen, for example oxygen, having a lone pair of electron, if these lone pair electron can be present in p orbital, unhybridized p orbital, the lone pair electron that is present in unhybridized p orbital can take participation in the delocalization of the aromatic system. So in that case, the lone pair electron that is present in p orbital can be calculated, can be treated as pi bonding electron also. So in that case you can determine the either this compound is aromatic or not aromatic by taking this p orbital lone pair electron. So dear student, now I would like to determine either any compound is aromatic or anti-aromatic. You can use a formula. This is very important formula. 4n plus 2 is equal to number of pi electron. By using this equation, you will get the value of n is equal to 0, 1, 2, 3. If you get the value of n, a positive integer, either it is 0, 1, 2 or 3, something like this, then you will be sure of that this structure is a aromatic. So you can consider, these are the example that you can consider. In case of benzene, okay, the number of pi electron is 6, so 4n plus 2 is equal to 6, the value of n is equal to 1. So you have got here the value of an integer, so this is aromatic. At the same time, this is the structure of naphthalene. In that case there are 10 number of pi electron, so 4n plus 2 is equal to 10, so the value of n is equal to 2. This is also another integer, so this is also aromatic compound. In case of naphthalene, 4n plus 2 is equal to 14, there are 14 pi electron available here, you have already seen in the structure. So the value of n that you have determined in that structure is n is equal to 3. So you can say this is also a aromatic compound. Now just you consider this structure. In that structure the value of 4n plus 2 is equal to 6, as there are 3 pi bond, so there are 6 pi bonding electron must be present in this structure. In that case the value of n is equal to 1. So as you can get the value of an integer, so you can say this is also an aromatic compound. Now look at the structure. This is basically the structure of furan, and this is clear to you that there are 4 pi bonding electron is available here. So this is basically oxygen. You know very well oxygen has 2 lone pair of electron, right? One lone pair of electron is present in the p orbital. This oxygen is basically sp2 hybridized. As it is sp2 hybridized, it must contain a perpendicular pz unhybridized orbital. One lone pair electron is present in unhybridized p orbital, right? You have already seen. And another lone pair of electron is present in sp2 hybrid orbital. So you know very well lone pair of electron that can be present in p orbital, unhybridized p orbital, it can participate in pi, it can act as a pi bonding or electron. So it can treat it, you can treat it as a pi bonding electron. So at the same time it can take participation in that case. So you can say the number of pi electron in that case is 6, 2, 2, and this lone pair electron also added here. So you can get 4n plus 2 is equal to 6, and so you'll get the value of n is equal to 1. As you get the value of an integer, so you can say this is also aromatic compound. Now look at the structure. Okay, so the number of pi electron is here 2, right? Number of pi electron is here 2, and the value of n is equal to 0. 0 is also an integer, so this is also an aromatic compound. But if this carbon is not positive, just you consider, if this carbon is not positive, this is basically cyclopropenyl cation, right? If this carbon is cyclopropene, then in that case this carbon will not become positive in charge. So when this carbon is not positive in charge, this carbon is basically sp3 hybridized. In that case, though it contains 2 number of pi electron, it would not be a aromatic compound. But this is aromatic because first concept is there the value of n is equal to 0, you have got a number of pi electron is 2 and the value of n is equal to 0. That's fine. At the same time all the carbon are sp2 hybridized. When this carbon become cation, when this carbon become cation, the hybridization of this carbon will be changed. The hybridization of this carbon will be changed from sp3 to sp2. So in that case, you can say that all the carbons are sp2 hybridized. At the same time, the number of the value of N is also integer. So you can say this is an aromatic compound. So all the carbons, all the structure that I have written on the board are sp2 hybridized. So the cyclic organic compound containing 4n plus 2 or Huckel numbered delocalized pi electron that becomes itself more stable and gives special substitution reaction are aromatic compound, you know. So again say the cyclic organic compound that basically contain 4n plus 2 or Huckel numbered electron which make itself more stable, and the cyclic organic structure that also undergo or participate in special types of substitution reaction. This type of compound is called basically aromatic compound. Now what is aromaticity? Aromaticity is basically the properties, the criteria that is related with the aromatic compound is basically called aromaticity. So the properties that is related with the aromatic compound to determine either any compound is aromatic or not aromatic. What are the criteria? What are the properties? Or which what are the properties that makes the aromatic compound more stable? What are the properties that makes the aromatic compound to participate special types of substitution reaction? These type of properties basically included into the aromaticity. Now substitution in benzene and its orientation. This is benzene, this is toluene, this is phenol, and this is benzaldehyde. So dear student, here this hydrogen atom is replaced by CH3, then it becomes toluene, and when hydrogen atom is replaced by OH, then this structure become phenol. When this hydrogen atom is replaced by CSO, in that case it will convert it to benzaldehyde. So these are the compound, these are the product that can be produced after the substitution of hydrogen by different types of group. So these are called basically mono-substituted product or mono-substituted benzene. Okay, the reactivity of this type of compound basically depend on this substituent. Okay, so the reactivity of this type of substituted compound or product or benzene will not be equal just like as the benzene. It can be vary. Basically this should be dependent on this group. Okay, sometimes this type of group can donate electron towards the benzene ring. It can increase the electron density into the benzene ring. If it increases the electron density into the benzene ring, then benzene ring will become activated, and in that case benzene ring will be more reactive. Okay, at the same time CHO or NO2, something this type of group when attached with the benzene, it can withdraw electron from benzene ring. In that case benzene ring will become deactivated and less reactive. Okay, so basically the reactivity completely depend on this substituent. For example, nitrobenzene has less reactivity than benzene. At the same time toluene or phenol, they are more reactive than benzene. So dear student, now induction effect. When sigma bond between carbon and halogen or X is any element, it can be halogen or any electronegative element, is polarized by X, then it is called induction effect of X atom. So the point that should be noted here, induction effect is completely related with sigma bond, not in pi bond. Okay, not with pi bond. This is completely related with sigma bond. Okay, it can be two types. One is positive induction effect and another is negative induction effect. In that case the sigma bond must be in between carbon and the electronegative element or carbon and the electron donating group. It can be two types. One is positive induction effect and another is negative induction effect, and this is denoted by I. In case of negative induction effect it will be denoted by minus I. In case of positive induction effect it will be denoted by plus I. Okay, now what is positive induction and what is negative induction effect? So if in sigma bond when carbon is attached with the electronegative element, for example, just you look at this bond. Here this carbon atom is attached with electronegative element. So as it is electronegative element, it should shift the electron density towards itself. By this way it will become negative in charge and it will become partially positive in charge. So if electron density shift towards electronegative element, in that case carbon atom will lose electron, or the electron density on the central carbon atom will be reduced. So this type of effect is negative induction effect and denoted by minus sign. And on the other hand, if the carbon atom is attached with electron donating group, for example R is alkyl group, you know, alkyl group, electron donating group. So in that case alkyl group will donate electron towards the center, towards the carbon atom. In that case the electron density will increase. Okay, so this type of effect is called positive induction effect. So if carbon loses electron, reduce electron, so this is negative induction effect. Or if carbon have electron from electron donating group, this type of effect is positive induction effect. So I hope you understand this. Mesomeric effect. Mesomeric effect is completely related with the pi bonded electron or the lone pair of electron, whereas induction effect was related with the sigma bonded electron. It can be two types and it can be denoted by capital M. It can be two types. One is negative mesomeric effect and another is positive mesomeric effect. So for the first time, negative mesomeric effect, the pi bond electron between carbon atom and more electronegative atom like oxygen is become polarized and pi electron density is shifted toward electronegative element, is called negative mesomeric effect and denoted by minus M. So if there is a bond, if there is a double bond, if there is a triple bond in between a carbon and the electronegative element, for example you can consider this type of example. In that case there is a double bond in between carbon and electronegative oxygen atom. As oxygen atom is electronegative, so oxygen will shift the pi bonded electron towards itself. By this way, this type of effect is basically called negative mesomeric effect. Here also nitrogen will shift that pi bonded electron towards itself, and this is another example of mesomeric effect, negative mesomeric effect. And here nitrogen, oxygen, as oxygen is more electronegative than nitrogen, so oxygen also shift the pi bonded electron towards itself. By this way, this can be another example of negative mesomeric effect. Now positive mesomeric effect. This is completely related with the lone pair of electron, lone pair of electron of electronegative element. We know very well oxygen, nitrogen, sulfur, they are, all of them are electronegative element and they all contain lone pair of electron. So when the lone pair of electron of electronegative atom shift towards the carbon atom, when this lone pair of electron that is present in electronegative element, if they shift towards the carbon atom, then it is called negative mesomeric effect. Just you consider this example. Here oxygen has two lone pair of electron. If this lone pair of electron is shifted towards this carbon, then you will get positive, this type of effect is positive induction effect. Here also nitrogen donate electron towards this carbon, so this is another mesomeric effect example. And here also this is basically a conjugated system. Here oxygen, lone pair of electron, of oxygen shifted towards this carbon and the bond shift towards this. So this is positive and negative induction effect, and the positive induction effect is denoted by plus M and negative induction effect can be denoted by minus M. When any group having positive induction effect plus I or positive mesomeric effect plus M is attached with the benzene ring as first substituent, it supply electron density in the benzene ring. This added electron takes part in delocalization of pi electron and participate in resonance. In that case, electron density in ortho para position will be increased and electrophile should be directed towards ortho para position. This type of group is called ortho para reacting group, and these are also called benzene ring activating group also. Okay, so what is ortho para reacting group? Basically these are the group, these are the example. And this type of group, if this type of group is attached with the benzene ring, they will supply electron density to the benzene ring. Again say, these are the group, if they attached with the benzene ring, by positive induction effect, by positive mesomeric effect, they will supply electron density towards the benzene ring. Hence, for this reason, the electron density in the benzene ring will be increased. Especially electron density in the benzene ring will be increased in ortho and para position. As electron density in ortho para position will be increased, so when an electrophile will attack this benzene ring having this type of group, then this electrophile will be directed ortho and para position. As they direct any electrophile in ortho para position, that's why these are called ortho para directing group. Again, as they donate electron towards the benzene ring, as they increase the electron density in the benzene ring, they are also called benzene ring activating group. Meta directing group, this is basically due to the negative mesomeric effect, which one is can be denoted by -m. These are the group nitronium ion CHO COOH. If this type of group is attached with the benzene ring, then they can withdraw electron density from the benzene ring. As they withdraw electron density from the benzene ring, so the electron density in the benzene ring will get reduced. So take participation in delocalization, the electron density will get reduced. At the same time, to take part in resonance, the electron density will also get reduced. So as there is a reduction of electron density from the benzene ring, so benzene ring will become less reactive. At the same time, benzene ring will get deactivated. So meta directing group are also known as benzene ring deactivating group. While meta directing group is attached with the benzene ring, this type of group are attached with the benzene ring. In that case, it is clear from resonance that in ortho para position they produce partially positive charge. So electrophile should not be directed at ortho para position as their presence partially positive charge. So electrophile should be directed at meta position in case of meta directing group, and that's why these are called meta directing group. So now effect of methyl OH and NH2 groups in benzenes. You know very well all the groups are ortho para directing group. Now I would like to explain why these are called ortho para directing group from their resonance. I have drawn here resonance structure for methyl, resonance structure for OH, and resonance structure for NH2. For the first time, I would like to explain the resonance structure of methyl. Okay, due to the hyperconjugation effect, this bond will shift here, and when this bond will shift here, in that case, this bond will shift to this carbon. When this bond will shift to this carbon will be negative in charge, and this is ortho position. So the point that you must have to noted or notice that which of the position become negative in charge. So when this bond shift here, this carbon atom will become negative in charge. Okay, so the carbon having negative in charge with 2 electron, these 2 electron will shift to this carbon, and for this reason they produce a bond. This bond basically, when this bond will form, this bonding electron will shift to this carbon. Okay, when this bonding electron will shift to this carbon, then this carbon, the position of this carbon is para position, you know very well. So the para position will be negative in charge, having 2 electron. This carbon will be negative in charge, and then this carbon atom having 2 electron, these 2 electron will shift to this carbon and they produce a bond. This is basically the bond. After the production of this bond, this bonding electron will be shifted to this carbon. As a result, this carbon atom will be negative in charge. Okay, this is ortho position. Okay, after that, this carbon having 2 electron, these 2 electron will be shifted to this carbon, and when these 2 electron will shift to this carbon, they produce a bond. This is basically this bond, and after the formation of this bond will be shifted to this carbon. So they produce a bond in between carbon and hydrogen atom, carbon and hydrogen atom. This proton atom will get 1 electron, and for this reason proton will be converted to hydrogen atom and they produce a carbon hydrogen bond. So the effect that is effected, basically act here is positive induction effect. So when methyl group is attached with the benzene ring, they are basically act positive induction effect, and due to this positive induction effect, methyl group will supply electron to this benzene ring. For this reason, electron density in ortho para and ortho position will be increased. For this reason, ortho, para and ortho position will be become negative in charge. So as they are negative in charge, electrophile, you know, electrophile is a substances that has deficiency of electron, latency of electron, shortage of electrons. So when electrophile attract to this group, so it should be supplied, it should be directed towards either this position or this position or this position. I mean to say it should be directed in ortho, para or ortho position. So at the same time, if you consider the example, the resonance of which oxygen atom has a 2 lone pair of electron. So here basically act the effect, which effect is called positive mesomeric effect. Due to positive mesomeric effect, it will share one pair of electron to here and they produce a bond. Okay, after the formation of bond, this bond will be shift here. Okay, for this reason this carbon will be negative in charge. This is ortho position, you know. And similarly, just like as the resonance structure of methyl, this will also happen. At the same time, in case of NH2, there also presents a lone pair of electron, and they are also act positive induction, positive mesomeric effect. Okay, and the resonance structure of which and NH2 just like as CH3. So I don't like to explain the resonance structure of which and NH2. Now the point that I would like to mention for further time is, if you analyze all the structure, all the resonance structure, both methyl, OH and NH2, then you will get structure 3, structure 2, structure 2, structure 3, 4, 2, 3, 4, 2, 3, 4. You will get ortho, para, ortho position are in negative in charge. That means there is increase in electron density in ortho, para position. So electrophile should be directed in ortho, para position, and that's why this is basically the main reason. For this reason, these are called ortho, para directing group. So as they are ortho, para directing group, so when they react with different types of electrophile, electrophile should be directed in ortho, para position. So during the time of nitration of toluene, this nitronium group, as it is a electrophile, NO2 as a electrophile, it should be attacked ortho position and para position. So they are produced ortho product and para product. At the same time, during the time of nitration of phenol, as nitronium ion is electrophile and this is ortho para directing group, so they are produced ortho product and para product. At the same time, for in case of aniline, when chlorination reaction will be happen, so chlorine atom should be attacked chlorine attacked in ortho position and para position. So by this way, ortho and para product can be produced. Okay, so dear student, you know very well NH2 is a ortho para directing group. Though this is NH2, this NH2 is ortho para directing group. During the time of nitration, it will give product at meta position. So this is basically why this happened. Okay, during the time of nitration, there is a chance to be protonated this NH2 group. So again say, during the time of the nitration reaction, there is a chance to become protonated this NH2 group. When this NH2 group become protonated, it will receive a proton by using these 2 lone pair electron. So these 2 lone pair electron have no chance to take part to supply itself towards the benzene ring. So for this reason, it cannot supply electron to the benzene ring. So in ortho para position, there has no chance to produce negative charge or increase electron density. On the other hand, there can have, as these nitrogen atom become positive in charge, so there can there is a chance to create positive charge in ortho para position rather than negative charge in ortho para position. So in that case, it will show product in meta position. So dear student, to produce ortho para product, if you want to produce here ortho para product during the time of nitration of NH2 group, you have to carry out the reaction by protecting group. You have to protect this group, NH2 group. You must have to protect here. So if you want to protect this NH2 group, you have to, this NH2 group can be protected by acylation. This is the acylation reaction. Okay, you know this is a cell compound, this is ethanol chloride. When this reaction is happened or carried out, one hydrogen atom should be replaced by CH3CO group, and by this way NH2 group will be converted to NHCOCH3 and they produce a product. This product is now named acetanilate. By this way NH2 group become protected. Okay, after the protection of NH2 group, if you carried out the reaction, then ortho and para product will be produced here, and after the production of this product, finally you must have to deprotect this compound. NHCOCH3 group you have to convert to NH2 group. Okay, if you want to do this, you have to add here acetic acid in addition with water, and after that this NHCOCH3 group will be converted to NH2. At the same time, this NHCOCH3 group will convert to NH2. By this way, from this product they are produce a para product, and from this product they are produce a ortho product. So this is the way to produce ortho para product during the time of NH2 group, during the time of nitration. Okay, so directly if you carried out the reaction, there will produce meta product, and if you want to produce ortho para product, you must have to carry out the reaction by protection. So dear student, now effect of NO2 CHO groups in benzene ring. You know very well, NO2 CHO COOH, these are basically benzene ring deactivating group or meta directing group. So now I would like to explain why these are called benzene ring deactivating group or meta directing group. This will be clear from their resonance structure. I have drawn here two resonance structure. This is resonance structure for NO2 and this is resonance structure for CHO. Okay, from this resonance structure, this is clear to us that from 2, 3 and 4, the ortho para ortho position are positive in charge. Positive in charge and positive in charge. Positive in charge and positive in charge. So as ortho para position are positive in charge, so when electrophile attack to this group, it should not be directed to this ortho para position, because there is a latency of electron, there is a shortage of electron, there is a deficiency of electron. So in that case, if electron attack to this group, electron will be directed only meta position. So meta position is not positive in charge. So there is a little bit chance to have electron in meta position. Basically in meta position. For this reason, electron should be directed to this meta position. So as they withdrew electron from this benzene ring, so look at the resonance clearly. Okay, NO, as oxygen is electronegative element, you know, due to the electronegativity of oxygen, this pi bonded electron will be shifted towards this oxygen atom. That's why this oxygen will be negative in charge and this carbon will be positive in charge. When this nitrogen become positive in charge, then this bond will be shifted towards this. Okay, this type of effect is called negative mesomeric effect, and due to this negative mesomeric effect, electron density from benzene ring will be withdrawn. Okay, so by this way, this position will be positive in charge. At the same time, when this position will be positive in charge, then this bond will shift here, and this para position will be positive in charge. At the same time, when this para position will be positive in charge, this bond will be shift here. As a result, this position will be positive in charge. Okay, when this position para ortho position will be positive in charge, then electron, this bond will be shift here. Okay, and this bond will be shift or come back to its original position. So by this way, this is the resonance structure of CHO is completely similar to this NO2. Here also there is a effect. That effect is called negative mesomeric effect. Both negative mesomeric effect and both negative mesomeric effect is applicable here. So the main point is that 2, 3, 4 structure ortho para position are positive in charge, so electrophile should be directed in meta position, and that's why this type of product can be produced here. So dear student, after the lecture you will be able to know details about the orbital structure of benzene, aromaticity and Huckel rule, ortho para meta directing group, induction effect and mesomeric effect, in addition with different topics. Basically these are the main topics. Okay, these are the main topics. Okay, thank you.